There we go. Right. Workbook, physics, materials. Yeah. Okay. Specific heat capacity. Can I write that down, please? Oh dear. Got that? Yeah. And that?
Yeah.
Yep. Okay. Why does metal feel colder than plastic? Now, it's a little bit strange because if you have some metal, let's say its temperature is 10 Celsius, and you have some plastic, and its temperature is 10 Celsius, the metal feels colder, doesn't it? And also, water at 10 Celsius is pretty cold. You know, if you put your hand in water at 10 Celsius, it'll feel pretty cold. But how come that feels colder than air at 1 Celsius? You know, would you rather be in air at 1 Celsius or in water at 10 Celsius? Yeah, but the water is warmer. You know, so there's something strange going on here. In other words, temperature is not quite enough. We need another way to talk about heat and temperature. Metals feel hotter sooner than plastics. In other words, metals get hotter quicker. And in fact, it's because metals are a conductor, something you've learned about in chemistry, and plastics are an insulator. So in other words, different materials have different abilities to take heat quickly or slowly. So some materials can take heat in quickly, and some materials take heat in slowly. So a metal can take the heat energy in quickly. Plastic takes the heat energy in slowly. Water can take the heat energy in quickly, well, compared to other things, perhaps. So this gives us our first definition. We need this thing called specific heat capacity. And basically, it's a way to tell how quickly a material can take energy in the form of heat. So the specific heat capacity of a material is how much energy you need to increase its temperature by 1 degree if you have 1 kilogram. So it's like how many joules will you need if you want an extra Celsius if you have a kilogram of the material. Okay, so that's what's called the specific heat capacity. Got that? So there's a small question what I want you to do now for me is let's try and figure out the units here. So, okay, it's the amount of heat energy you need for 1 unit mass and 1 unit of temperature. So what do we think the units might be? If we look at the definition, what might the units be?
Grams per Kelvin.
It is going to be per Kelvin, yeah, but I don't think it'll be grams per Kelvin. Because you haven't included joules in it, you know, and there's you're looking for the energy. So what do we think?
Joules per kilogram per Kelvin.
Yeah, that's it, yeah. Joules per kilogram per Kelvin. Yeah. So if you want, you can say the unit is The heck? Ooh. Where's my pen gone? Pen. Oh no, it's doing that thing again. How did I... Does anyone remember what I did last time to get rid of this?
I think Lucas helped.
Yeah, this is when Lucas was here, wasn't it? Mm. Oh, goodness sake. Let's keep pressing. Oh, got it. Okay, it's... Yeah, okay. So if you press J, you can turn it on or off. Okay, that's now. I've learned that now. That's good. Okay, so it's joules per kilogram per Kelvin. Okay. Right. So if you think about it, you could work it out a formula. You know, suppose that you didn't. Okay. Well, actually, let me just clear up things before I go ahead. So this is what specific heat capacity is. You imagine that you have 1 kilogram. Okay. And you want to increase the temperature by 1 Kelvin or 1 Celsius. It's the same thing. So we'll just say 1 Celsius. You have to put some energy in. This is called the specific heat capacity. Okay. So for some materials you need a lot of energy, and some you'll need a little amount of energy. So what material might need a little amount of energy to warm it up by 1 Celsius? What type of material do you think? A metal, yeah. So like maybe something like copper. Okay. And what material might take a lot of energy to heat up? What would you say? Plastic, yeah, maybe air, yeah. Maybe some wood, something like this. Now suppose you didn't have 1 kilogram, suppose you had m kilograms, and suppose you wanted to increase it by some temperature, maybe not 1 Celsius, maybe you want delta T to Celsius. There's a formula to work out how much energy you need to put in, and you can actually work it out if you think about the units. Not surprisingly, it'll be equal to m times c times delta theta. Because if you think about it, if I was to divide Q divided by m delta theta, I would get C. So we said C is energy per mass per temperature per Kelvin, you know. So it kind of makes sense that this has to be the formula for Q just from the units. You don't need to write that down because I have it here in the slide. So the energy required to increase an m kilogram mass by a temperature of delta theta can be found from the formula Q equals mc theta, where C is the specific heat capacity of the material, and it's different for each material. Got that? Yeah? I'll remind you that the link is on Moodle now for the draft. Yeah. Okay, continue. So the next thing we have to have a look at are some values of specific heat capacity. So what one do I have first here? Water, liquid. Now this is interesting. The specific heat capacity for water, it's different if it's a solid, liquid or gas. So when it's a liquid, that's 4181. Now that's a lot. If you had 1 litre of water, it's 1 kilogram, that's about that much water there. Okay. If you want to increase that bottle of water by 1 Celsius, you will need 4,181 joules. That's a lot of energy just to get 1 Celsius. You know, if you want to increase it by 90 Celsius, you would need 90 times that. So it's an awful lot. Okay, so if we can write these values down, the first one is liquid water, 4181. Next one. Next one is ice. So ice needs less energy to warm up. It needs 2,110 joules per kilogram per Kelvin. And do you mind letting Chow in? Chow, you're late. Come on. Okay, got that one? Next one is steam, 2080. Okay. Next one is copper. It's only 385. Yeah. Next, milk. Let's put milk in the form. 2,850. Alcohol, 2,300. And two left. Lead is 129, and air is actually 1,012. It's pretty big. Yeah. Yeah. Okay. So let's see what I have next. You getting these, Chow?
Mm-hmm.
You got them?
Yep.
Yep. Okay. So why do materials have different heat capacities? Any ideas? Like, why would lead be so different to liquid water? What is it about lead that makes it different? It's complicated, and it's something we might look at later, but it's not a clear reason why. You know, you can get an idea. You know, the copper is a conductor, so it's quite low. But I mean, I don't know. To me, this seems quite big for air. I would have thought air would have been easier to heat up than, say, like, I mean, air is kind of the same. It's kind of half the amount of ice. You know, it seems like air should be easier to heat up. You know, so there's many complicated reasons. Maybe air is so high because the density is so low. It's difficult to heat it up. You know, it's quite complicated. Anyways, let's have a look at a question now. We'll do this one together. How long would it take to boil enough water to make a cup of tea by using a small 1 kilowatt electric kettle? And we'll have to estimate some things. I don't give you enough information. So, this is what we want to do. We want to make a cup of tea. So we need some water, and we have our electric kettle. So we need to have enough water to be able to put into the cup of tea. So let's estimate some things. How much water do we think we need? What would you say the mass is? You know, 0.2. Okay. Right, now, the specific heat capacity of water is 4181, I think I said, wasn't it? Joules per kilogram per Kelvin. Right. We now need to estimate how much we have to change the temperature. So what temperature would we like the water to be at? 100. 100, yeah. What temperature do you think it started at, roughly? Now, come on. How long have you been in Ireland? The water's not 25 Celsius when it comes out of the taps here now. Think again. You turn the cold tap on to get water for tea. How hot is that water? I think 10 is more like it, yeah, perhaps. So if we go from 10 to 100, that's an increase of plus 90 Celsius. Yeah? Right, so we have our formula. Let's calculate how much energy we need. So we need mc delta theta. So that would be 0.2 times 4181 times 90. So that's how much energy we need. So yeah, if you can just tell me that please, and then we can get the next part. 75258 joules. Now, let's see how long it takes for this to happen. So we know that power is work over time. So time is work over power. And in the question I tell you the power is 1 kilowatt. So that's 1,000 watts. What's the work being done here? Well, the work being done is putting heat energy into the water. So what number should I put on the top here? What do you think? Yeah, 75258. Okay, so what answer do we get here, please? It's going to be 1, 2, 3. It's going to be 75.3 seconds. So that is 1 minute and 15 seconds to boil the water. Now that's quite quick, but remember we're only using 200 grams of water. It's not much water, so it should boil pretty quick, even in a small electric kettle. Okay. Right, so that's our first example. So you were given this, and you were also told the power as well. You were told the power is 1 kilowatt, and we wanted to calculate the time. Okay, so if we can write this one down, and we'll have a look at another example. Do you think in real life it will take longer or shorter than this time?
Shorter.
Longer. But does anyone know why I'm saying longer?
Heat loss.
Yeah, some heat is lost. Not all the heat energy goes into the water. Where does some of the heat energy from the kettle go? Where do you think? Not all the heat energy heats the water. In the air around the kettle, correct? Yeah, where else? Where else? The actual kettle itself, yeah, the plastic kettle will warm up too. So, I don't know, I think in real life, maybe it'll take 2 minutes. Does anybody have a kettle in their apartment? You do?
Yeah, it usually takes I assume this would be short, because it takes 20 seconds.
Oh, I see. Well, my kettle is a very small one. It's at 1 kilowatt. Yours is probably like 2 or 3 kilowatts, so it'll take half the time, If you could measure 1 kilogram of water poured in and time it, see how long it takes. If it's a 2 kilowatt kettle, is it a big or small one?
It's a big one.
So it's 2 kilowatts. So it should take half this time if you use 200 grams. So you said it like
27.
yeah, that sounds about right then, yeah. And this is why you were saying that you thought it takes shorter, because of real life experience. Yeah. In my example, I was using it. You know what I mean by a travel kettle, like the little electric ones. Yeah. Okay, you got this? Yep. So next now. Now this one here. 100 gram block of ice, so a little block of ice, well 100 grams is pretty big, its temperature is -10, it's left out in the sun and it warms up until it reaches -1. How much energy do you need? Okay, so do we know the mass? We do. Do we know the C? What is it for ice? Something like 2000, is it?
2001.
Yeah, and careful now, what's the change in temperature? What's the delta theta? What's the change in the temperature? 9. It goes from -10 to -1. That's a 9 increase. I think you can give me this answer. What's the energy? Are you in this building or the other building? You live in this building? No, you don't.
I live on.
Does anyone actually live on campus? Andek, do you live on campus? No. No. Nobody here. You do. This building or the next building? That's the other building. So I was going to ask you to get your electric kettle, and we could time it. But do you have an electric kettle? You do. Okay. Right. Do we get an answer here?
1,889.
Is that what you got as well? 1,889? Okay. Right. Now I'm going to change this a little bit. I'm going to make it more real life. Let's make it real life. So let's say we take a room like this, okay? We roughly estimate the size. We'll imagine this room that we're in is like a box. Okay, how big do we think this box is, roughly? So what would we say? It's like, I don't know, 4 meters by 6 meters maybe. And how high would you say? I know here is higher than here, so an average height of 2 meters, would we say? 2 meters? Yeah? Okay. Right, now, obviously this room is made of air. Okay. Now, it's not only made of air. There's other things in the room as well, like wooden furniture, people, stuff like this. Okay. But just to make the problem easy to begin with, we just imagine the room is empty and the only thing in it is just air. Okay. So let's say somebody left the window open and it's left it open overnight, so now the room is cold. We'll say its temperature is 10 Celsius. And we would want to increase the temperature, what would be a comfortable temperature? 20. We'll say 20, okay. Yeah. And we can do this with a little electric heater. And we'll say the power of the heater, these heaters are usually like 3 kilowatts. Okay? And the last thing you need to know is the density of air. So the density of air, I think we said it's something like about 1.3, I think. We'll say it's 1.25 kilograms per meter cubed. So I've given you enough information there to work out how long it will take to heat up the room. You actually have enough information. It's very similar to my electric kettle example. The only thing I recommend that you do first, the first thing you should really do is calculate the mass of the air. Then, once you have that, it's not so difficult to get the time taken to heat the room up. I'll give you a minute to try this before I do it. I think you can get this. If it helps, you should also remember density is mass over volume. Okay, so have you got part 1 done? Did you get a mass of 54? Good, okay. Now on to part 2. You know that power equals work over time. So time equals work over power, which equals work over 3,000. Now what work is being done? Yeah?
48 times 1.25 is 60.
Thank you. I did this in my head. You don't be so shy. I don't have a calculator, so don't think you have to be friendly to me. It's okay, you know. Right, what work is being done? What's the work being done? Or what's doing the work here? Yeah, but I mean, what thing or what work is being done? The heater, yeah. The heater is giving heat energy to the room. So we need to work out how much energy. That's the Q. Now you have a formula for that. It's MC delta theta. So that's M. Oh, yeah, I gave you the C, didn't I? What was it? 1012? Or 20?
12.
12, okay.
Yeah.
And what's the delta theta? 10. Okay, so what answer did you get here?
607,200.
60. Yeah. That big? That's pretty big. Oh, over 3,000.
Oh.
Okay, so
202.4.
202.4 seconds. So, what's that? 3 minutes and 22 seconds? Is that right? About? Yeah? Now, in real life, it'll take longer to heat the room. There's two big problems that I didn't consider in my simple picture. What are they? So it'll take much longer than this. So there's 2 big things I didn't include in my picture. What's that? What's missing from this picture? Yeah, so firstly, the mass is not 50 or 60 kilograms because you have furniture, you have carpet, you have people. So you need to consider that there's also other things that need to be heated up in the room. Okay, so that means this Q here is too small. You need much more. Now there's also one other thing I forgot that's very important. Something to do with the walls.
Temperature of the walls.
Not quite that. Not quite that. Something else. Not quite that. Yeah, but why is that important? I'm sure somebody knows. No? Okay, I'll tell you. So when you heat the room up, some of your effort is going to escape. So the problem is, as you're heating the room, some heat is also leaving the room via the window or under the door. Makes it harder for you to heat the room up. So in other words, your efficiency, maybe it's only like 50%, or maybe even in some rooms it's only like 25%. You know, so you put 4 joules of heat energy in, but then pretty quickly 3 joules leave, and only 1 joule stays. So I would think you would have to make the mass much bigger and the efficiency as well. So you know, it could be that this needs to be 10 times bigger once you consider all the other factors as well. But it's going to be at least 3 minutes if everything is perfect, which is never perfect. Okay, right. A physics student is making a latte. He mixes 200 grams of hot milk at 27 Celsius to 50 grams of hot coffee at 80 Celsius. And I know coffee is not the same as water, but it's pretty similar. Like if you think about what coffee is, it's mostly just water with some coffee beans mixed in. Okay, so we'll imagine coffee is like water. What is the final temperature of this delicious, warm, steamy latte? Okay, so you're mixing milk and coffee, and you want to know what the temperature is at the end. Now, of course, it'd be nice if it was as simple as 27 plus 80 divided by 2. Of course, it's not that, because which do you have more of? Do you have more milk or more coffee? You have more, and this one here, it's a latte now. Yeah, you have 200 grams of milk and 50 grams of coffee. So do you think the final temperature will be closer to 27 or closer to 80? 27. Why is that? Yeah, because you have so much more milk than you do coffee. You know, like if you had 600 grams of milk and 1 gram of coffee, the effect of the 1 gram of coffee will be nothing on the temperature, you know. So if we were to guess an answer before we calculate it, what do you think might be a reasonable answer to get? Somewhere near 27. So what would we say?
35.
Yeah, maybe something like 35. So we'll mix 200 grams of milk with 50 grams of coffee. Let's see what temperature we get at the end. So let's draw the picture. Now, for my pictures, I like to draw the two separate. So I imagine here's the milk and here's the coffee. Of course, in real life, you mix them together, but just for our picture, it's easier just to think of it like this. Right, so you have 50 grams and 200 grams. And the coffee is like water, and the milk is like milk. What temperature did I say? It was 20, what did I say? 80 and 27. This is 80, and this is 27. Okay. Now this is at the start. Now at the end, you still have 200 grams of milk. True? And you still have 50 grams of coffee. True? But the temperatures will no longer be 27 and 80 because you've mixed them together. They'll be X and X. Now why am I saying they're the same at the end? Say again? Yeah, they're mixed into one thing now, so they should be the same temperature. You know, I know sometimes when you drink coffee, sometimes the coffee is a different temperature than the milk at the beginning. But if you wait a couple of minutes, they reach the same temperature. Okay, right, so that's X Celsius and X Celsius. And we imagine that the coffee cup has a lid on it, so there's no energy that escapes. So we keep it easy like that. And we want to work out what the X is. Okay, so think about it like this. The water starts at 27. Will it be warmer or colder than 27 at the end? Now you gave a rough answer. You said it'd be about 35. So it will be warmer. So this has gained energy. Okay. What about the milk? Will it be warmer or colder than 80? Colder. So this has lost energy. But remember we said it's inside of a cup. So no energy can go in or out. Right? So that means the energy that this guy got must have came from the energy this guy lost. Okay, so you can make this equation. The energy gained by the coffee must equal the energy lost by the milk. So far, is that okay? Alright, so what's the M for the coffee? 0.0, I think we said 50 grams, isn't it? Yeah. So that's right, isn't it? The C is 4181. Now we have to think very carefully. What is the change in temperature? So it starts at 27 and it goes to X. So it would be X minus 27 because the X is bigger than 27. That's the change. Okay. Right, now let's look at the milk. The milk is 0.200. What's the SC for milk?
2850.
2850. Now, careful. What's the change in temperature? And I should say, I like to keep these numbers positive. 80 minus x, good, because the 80 is bigger than the x. Now, you realise you're kind of finished, because this is a maths problem. You just have to solve this for x. So these questions in the exam, the students have a very hard time making this equation. But once you can carefully make this equation, then you're finished. You have the answer. You can work out the x. Okay. So let's solve this. Can somebody please just multiply? Maybe Siba, can you multiply those two, and then maybe Matt, can you multiply those two? What did I ask you to do? Left or the right? To right. Okay, sorry. What did you say? 517 times 80 minus x. 570. Oh, 70. Sorry, 570. Okay, and Siba? 209. Well, no, I should put it in. 0.05. X minus 27. Okay. So Siba, can you just do that answer times 27? And Matt, can you do your answer times 80? Yeah, what you get?
4560.
Oh, wait, Siba first. I don't want to get confused. I'm easily confused. 5?
644.35.
Okay. And that's 5. What did you get?
45600.
45600 minus 570x. Right. I will take everything to the left. So you have 209.05x plus 570x. So Matt, if you can do those two. And then Siba, 45600 plus 5644.35. So what you get, Matt? 77.05 x equals, Siba?
51244.35.
Okay. So maybe George, I'll pick on you. If I'll just do division here, 51244.35 divided by 779.05.
67.77.
Okay.
65.8.
65.8 Celsius. So your answer 35 is too small then. Okay. But I'm assuming everybody used their calculator correctly, so 65.8. It would have been a disaster if our answer was more than 80. Clearly we would have made a mistake. And if our answer was less than 27, clearly we would have made a mistake. Because that meant mixing the coffee and the milk made everything colder. Yeah, but colder than the temperatures of either of them at the beginning. You know, like if this is 27 and this is 80, and you mix them together, it can never be less than the 27 or more than the 80. Yeah. Yeah. Is that okay, guys? Chow, is it okay or confusing?
It's okay.
You missed the formula at the start. We did this formula, which I don't think you got. Energy equals mc delta theta. That was at the start of the lesson.
Mm-hmm.
So I needed that formula here. You can get it from the video later.
Mm-hmm.
You got this all written down, Kim? Yeah. Is it okay? Are you sure? Sibo, is this okay? Are you sure? Anda?
It's a bit long, but
It is long.
Yeah.
Students don't like this one in the exam. I'm not sure why, because to me it's just a maths problem.
It's not that hard. It's have to process it.
Yeah, processing, like all this work here.
Yeah.
Yeah. Students don't like that in the exam, you know. A lot of the times the students make a mistake before getting to the end here, you know. It's a pretty common enough exam question. They like to ask what's the temperature when you mix two things together. It usually comes up in section B though, usually. Okay. Right, one more example. How much warmer would a 10-gram lead bullet...
Sorry, quick question. Are we going to have these tables in our exam?
Have what?
These.
Oh, it'll be given to you, yeah.
Okay.
Yeah, in the question,
Right,
yeah.
right.
Okay, so what we have here, I'll draw it for you. You have a bullet from a gun. It's made of lead. It's 10 grams, and it's going 100 meters per second. And it hits into a wall. So obviously, it stops when it hits the wall. Okay, so there's like a hole here where the bullet is, smushed into the wall. Now, it might not shock you to know that this bullet, when it hits the wall, you know, you can see it in the wall, it'll be warm. So I'm sure you've watched horror movies before, haven't you? I'm sure. Zombie movies, perhaps. You know, you kill somebody in the cold, and you can see the steam coming out of their body from where the bullet pierced them. You know what I'm talking about? Or, you know? Can't you picture this in a movie? You shoot someone, they fall to the ground, they land in the snow, you can see the steam coming out. Or maybe you don't watch horror movies, no? Never noticed. You'll notice next time now. So, the reason for that is that the bullet has become warm when it impacts something. Now, why is that? Well, what energy does the bullet have here? Kinetic energy. Does it have kinetic energy here? No, it stopped. So that energy has to go somewhere. Where did it go? Heat. So the kinetic energy must equal the heat energy. So you can say a half mv squared equals mc delta theta. Okay. Now, you can cancel the m's. That's a half times 100 squared. What's it for lead? Is it 129? Delta theta. So delta theta, that is what's that, please? It's going to go in 5,000 550?
38.76.
So it's 38.7, so 38.8 Celsius. That's a lot. So if you touch the bullet and put it into the gun, the bullet's temperature is probably about 20 Celsius because of your fingers when you hold it, okay? So if it was 20 Celsius to begin with, it's 38 Celsius hotter at the end, so that's about 68 Celsius. Okay, so if this was 20 here, then it will now become 68.8 here. And that's quite hot. You know, you couldn't really touch that anymore. It'd be too hot to touch. 70 Celsius, you know, it's pretty hot. Yeah? Okay. You can write this one down, please. Got that? I don't think you'll get a question. You might get a question like this in the exam, but whatever question you get in the exam, it won't be to do with a bullet. Because when I was talking to the person who writes her physics exam in the UK, he says he has a rule that he doesn't put any weapons in his exam. So no bullets, no cannons, no arrows. So you shouldn't see any bullets in the exam. But the question could have been about a lead weight, something like this, instead of a bullet. Okay, right. So I'll let you try these for a few minutes, and then we can go on to the next lesson. So I'll just close this here. Oh, go on.
Oh.
Go, yeah, go.